Hi guys, in today's video we're going to show you the basic foundation of vector error correction model as well as vector autoregressive in theory and practice. And at the end of the tutorial we will show you how to implement those kind of model in Eviews. So we will start first of all with a theoretical part, and at the end we will show you a practical case, a practical situation in which we can implement a vector autoregressive and VAR model using Eviews. So first of all, we need to know that multivariate time series are different kind. We have vector error correction model that we will come a little bit sooner on it back. We have a vector error correction model. We have autoregressive distributed lag model, and we have error correction models. So that principal four time of vector of multivariate time series. So in VAR situation, we have, for example, a situation of two variable that we need to express each one in function of lags of the others. So we have, for example, we have prices on the market, and secondly, we have the demand. So we maybe need to express the demand in function of price and vice versa. So we can use this matricial representation in order to express a couple of variables represented by price and demand in function of lag lag vector of price and demand. So you have the error term as in linear regression, but the difference here is that we express many variables in function of order. In this case, we have expressed a variable in function of lag variable. So this is the reduced form. We also have a structural form of model that lead to autoregressive distributed lag model. XT and YT could be both integrated of could be stationary or both integrated of order 1. The residual are integrated are stationary. So we also have a situation in which both XT and YT are stationary. We have a conventional stationary bar. So we have also a situation in which both XT and YT are integrated of order 1. So when there exists a beta, coefficient beta, so that xt minus b yt minus beta xt is stationary, we have a problem of spurious regression. So in the situation in which both variables are integrated of order 1 and there exists a beta, so that xt minus beta yt by minus beta xt are stationary, we need to express a error correction model. So in a situation in which we have only one cointegration relation, this relation when beta exists, so that yt minus beta xt is stationary, we can say that there exists a cointegration relation between xt and yt. And in the case which we have only one cointegration relation, we should estimate a Engle and Granger test. We should make a Engle and Granger test to do that, to know that. So in the case in which we have more than one cointegration relation, we have to estimate a vector error correction and Johansen test. So vector error correction, Engle and Granger test is in the situation in which we have only one cointegration relation, and when we have more than one cointegration relation, we should run a vector error correction model and Johansen test. So we can have a situation in which we have more than two variables. So we have variable x1, x2, still xk. We have k variable, and in this situation, we have a var which is not just a relationship between two variables as previous situation that we presented to you in this tutorial, but we have multi relationship between variable and last variable. So we have a structural form of var, which is a situation in which we have all our variables that are in which x1 and x2 are integrated of order 1. We have a structural form of var that is given in your screen. And in this case, we talk about autoregressive distributed lags in our models. So in other situation, we what is var p, var of order p, instead of var of order 1. If we have, we take a situation of var of order 2, we can estimate our variable in function of 2-degree lag. So we estimate our variable, our couple of variable in function of lag variable of 1 period and lag variable of 2 periods. So in this situation, we have a var 2. So if we make a transformation, we can estimate this relationship so that any var p could be transformed in var 1. So we don't need to estimate in every term a var p. So this relationship permits us to transform any var p in var 1 by this transformation using companion matrix. So what is cointegration? As I told you very earlier in this beginning of this tutorial, there are two integrated of order 1 series xt and yt. If there exists a beta so that yt minus beta xt is stationary, we say xt and yt are cointegrated, or there is one cointegrating relation between xt and yt, and the state of xt minus beta of yt minus beta xt is stationary, which stationary is called the long run equilibrium between xt and yt. What do we run a cointegration test? So the method of Engle and Granger is given as so we fit yt in function of linear relationship of xt. So we fit with ordinary least square and we test if whether or not residual of this relation of this linear correlation estimation is stationary of order or stationary of order of or integrated of order one. So we should make sure whether or not residual of a linear regression between yt and xt is have an error term that is stationary or co-integrated of order or integrated of order one. How to test stationarity of error term or versus integration of order when we have decay Fourier test and augmented decay Fourier test. So decay Fourier test is based on the assumption that if there is no drift or there is no drift or a linear trend, we have a linear relationship of ZT, which is the error term of our previous regression. So ZT is equal phi ZT minus 1 plus another error term where YT is a white noise. So the decay Fourier test is based on the fact of the hypothesis H0 that phi1 equal 1 versus the alternative hypothesis phi is module is less than 1 or H0 mean ZT is a random walk while on the H0 ZT is a stationary autoregressive. So using this assumption, we can compute a test statistic and student statistic is not standard normal and its limited distribution is called decay Fourier distribution, which doesn't have a closed form representation. So we just simulate critical value of decay Fourier statistic in order to make a decision on whether or not our variable is stationary. So to capture the non-zero mean, we can write this from with a constant in our models, in our previous model. So there are also a situation in which we can capture a non-zero mean or a linear trend by adding a trend term in our relationship. So we can use the same principle in order to test the stationarity of or the cointegration of our models. So we have also a augmented decay Fourier test. The augmented decay Fourier test assume that xt or ut is the white noise by adding enough lag in the differential of the error term of our regression relationship. On the right hand side, this properly could be guaranteed approximately. So we have to choose the choice of lag by using many criterion like Akaike information criterion or other criterion in order to help us take a decision about our test. So in this situation, we have to recapitulate what we have said since the beginning. So we have a var p between give a relationship between two variable and lag variable. So we have a reduced form, we have a structural form. In the situation in which xt and yt are stationary, we have a conventional stationary var. And in the situation in which we have both xt and xt integrated of order one, and in the situation where there doesn't exist a beta, so that yt minus beta xt is stationary, we have a problem of spurious regression. So we can determine whether there is a spurious regression using augmented Tikefuller test. So the situation in which we accept the null hypothesis in the Tikefuller test mean that there is problem of spurious regression. So, what is really spurious regression? What is the manifestation of spurious regression? So we have Engle and Granger test indicate there is no beta zero, so that yt minus beta xt is stationary. We have an example: monthly salary at Microsoft and YT as a population in the developing countries series. Two series are totally uncorrelated. The two series are not, there is not possible relationship between monthly salary in Microsoft and the population in developing country, developing African city, for example. But the increase in xt and yt doesn't cause each other. So ordinary square of xt on yt will generate high R square because correlation, calculated correlation between the two variables is high, but ordinary least square is not reliable when spurious regression is present. So in the situation in which both xt and yt are integrated of order one, and there exists a beta zero, so that xt minus beta yt is stationary. In the situation we reject the null hypothesis in Tikefuller test, it means that we should make a error correction model that we will present to you in a moment. So what's error correction model? So we have a representation of our model in which we estimate our variable in function of lack of orders. So we have a simple classical var here. So if we substitute we substitute the expression yt, which is equal to the differential of yt plus yt minus 1, and xt equal differential of of xt plus xt at the time t minus 1. You obtain the current relationship that the term in red in your screen appear in the two relationship, which can signify that we can estimate uh, the differential of our two stationary variables in function of each other. That is error correction model. So in the case of structural VAR that is given here, you can also make a same substitution and have a similar term that appear in the two relationship between the differential of our variable. So which means that we can express the differential of our variable in a linear manner. So that is error correction model that we will present to you most widely in a moment. So how to fit error correction model? So Engle and Granger have two-step fitting. This kind of model, error correction model. So we first fit ordinary least square of regression of yt in function of xt. So in this linear ordinary least square that we fit, since xt and yt are co-integrated, so that alpha and beta 0 are co-integrated, we fit the relationship yt equal a certain constant theta multiplied by the differential of xt plus another coefficient multiplied by the error correction term, which is the residual of previous ordinary least square of our two variables. So this term, the term called the error correction term that we found in a previous relationship in red. That is the estimation of the differential of a variable in function of the differential of order, without forgetting the error correction terms. So that's the representation of error correction theorem. So to recapitulate ourselves, we can say that VAR model in VAR model, we have a reduced form and a structural form. In the case in which our two variables are stationary, we have a conventional stationary VAR. In the case in which we have our two variables integrated of order 1, in a situation in which our two variables are not co-integrated, we have a problem of spurious regression, and in the situation of cointegration, we need to estimate error correction model. And in the case we have only one cointegration relation, we have Engle and Granger test works. So what is there more than two? What if there is more than two variables? So we have x1, x2, and x3, for example. If we're confident that there wouldn't be more than one cointegration relation among terms, which means that cointegration is equal to 0 or 1. So Engle and Granger tests are fitted. We fit ordinary least square of third variable in function of each variable in function of order, and augmented decay Fourier test, and make augmented decay Fourier test on the residual. So if there is two cointegration relation in our variable, so there is a strong multicollinearity between the two first variables. So we have to estimate in the situation of which there exists a multiple cointegration relation between variable to make a vector error correction and Johansen test. So Johansen methodology has been made since 1988. So the drawback of Engle and Granger approach, what is it? It can only identify simple equilibrium relationship among the variable. If we have more than two variables in the model, then there is a probability that of having more than one cointegration relationship. So Johnson in 1988 proposed a framework of estimating and testing of vector error correction model based on vector autoregressive equation with which we can find out how many cointegration relations exist among variables. Johansen vector error correction model is more general for testing multiple cointegrating relationships when there are more than two variables. For k variable, we can have up to k minus one cointegration relationship. So in a k-dimensional vector error or vector autoregressive regression model with p-lags, we have a representation, the following representation of xt in function of lat vector. So matrices P1, P2, Pk are have a covariance matrix. So when xt is a vector of k times series at time t, and xt is a vector white noise with covariance epsilon. So if the variable from the VAR are cointegrated, the VAR model presented can be equivalently rewritten in the form of vector error correction as shown below, Engle and Granger in 1987. So we have a term in red which represents a error correction term, but in this case we have a coefficient, a matricial coefficient p that is being used in analog manner in the case of only two variables. So a k-dimensional vector error correction model for a VAR P process can be written as is given on your screen. So with the error correction term in red. So in the vector error correction, the differential of xt and its lat are all stationary. So pkk time multiplied by xt minus 1 is the error correction term, and the matrix pkk contain long run relationship. So the rank of this matrix is a number of cointegration relationships. So if there are R or integration vector, the matrix can be expressed as the product of matrices of order Kr and matrix of order Rk. So alpha contains speed of adjustment parameter which interpreted as a way with which each cointegration vector appear in the given equation. Beta contain coefficient of long-run relationship. So we have many situations. If the rank of matrix P is 0, it means that xt is integrated of order 1 and not cointegrated. So the vector error correction is reduced to the differential of xt in function of the differential of lack of our variable. So the differential of xt follow a VAR p minus 1 models. You can remember that originally xt follow the VAR x p models. So if a rank of matrix is maximum, it means that P was full rank, so that xt is stationary. If it's coarse, we can simplify analysis. You can simply analyze xt directly. So if we have a rank of our matrix between 0 and k strictly, there are R cointegration relation, and P can be written as a product of two matrices where beta has R linearly dependent column representing the cointegrating errors vectors. So you can notice that the products alpha beta is not unique, as you can see. But how to determine the number of cointegration relationship? The rank of the long-run impact matrix E equal to the number of cointegration, and it is evaluated to determine the number of eigenvalue that different from 0. And Johansen and Joselius in 1990 proposed two methods to determine the number of cointegrating relations. We have trace statistic based on likelihood ratio tests about a trace of the matrix. We have maximum eigenvalue statistic based on eigenvalue maximum obtained from estimation procedure. These cointegration tests are formulated in terms of estimated eigenvalue lambda E of the matrix E. So we have Johansen trace matrix, trace statistics. So the trace statistic consider whether the trace is increased by adding more eigenvalue beyond the earth eigenvalue. Consider the hypothesis. In our hypothesis, the rank is R0 or more than or superior to R0. The likelihood ratio test is given, and you can note that if rank is the rank of matrix is equal to R0, so all non-zero eigenvalues should all be close to 0, or a likelihood ratio statistic should be small that you cannot reject H0. So if rank of the matrix is superior to R0, then all non-zero eigenvalue should be non-zero but less than 1, and the likelihood ratio statistic should be larger should be larger. So Johnson maximum eigen statistic, it is sequential procedure to determine the number of cointegration. Consider the hypothesis H0 rank of P equal R0, or the alternative the rank of P is equal to R0 plus 1. The test statistic is given by negative t on multiplying the logarithm of 1 minus the likelihood of order R0 plus 1. So we can note that the test consists of ordering the largest eigenvalue in descending order and considering whether they are significantly different from 0. Suppose we obtain a n eigenvalue noted lambda 1 to lambda k. If the variable under are not cointegrated, the rank of p is 0 and all the eigenvalues should be equal to 0. Therefore, the logarithm of 1 minus lambda I equal to 0. So the asymptotic null distribution of both tests are not chi-square, but instead of complicated function of Brownian motion, and the critical value of the statistics are non-standard. Critical value of both statistics are provided by Johansen and Joselius of since 1990. So maximum likelihood estimation of cointegrated vector is the method required in order to estimate a parameter. Once we found the rank of matrix P, then the cointegrated vector can be written. So we have cointegration, the cointegrated relationship, the relationship between differentiated variable that are given in the relationship that you see on the screen. And in this relationship, we have the error term, which is Gaussian white noise. So reduced rank multivariate regression. Johnson derived the maximum likelihood estimate of parameter under the reduced rank restriction. So the estimate of beta coefficient are given in by the eigenvector associated with the eigenvalue, each eigenvalue. So we first estimate beta 0 using MLE block and in beta 0, and the MLE of the remaining parameter can be estimated by ordinary least square, since the variable are cointegrated stationarily. So we have the relationship that is given below. So we can know that Johansen approach estimate beta using MLE instead of ordinary least square, which use an Engle and Granger two-step as if R is superior to 1 may cause multilinearity. So maximum likelihood estimation, we consider two multivariate regression. The first is the differentiated regression, the relationship between differentiated vector and lags till order p minus 1, and we have the estimate of lag vector in function of differentiated lag vector. So in this situation, we we solve the relationship to denote the eigenvalue and eigenvector pair by that is given there. So we have to recapitulate. To recapitulate, we can say that we have the P model, we have the reduced form, we have a structural form, we have a situation in which both xt and yt are stationary. We have a conventional stationary VAR in this situation. But in the situation in which we have both xt and yt co-integrated, and there doesn't exist a relation beta zero, so that xt minus beta yt by so that yt minus beta xt is stationary. Have problem of spurious progression. But in the situation in which there exists a beta, so that yt minus beta xt is stationary, we have an error correction model. So only on cointegration relation, in the situation we have only one cointegration relation, we estimate a Engle and Granger test. In the situation in which we have many cointegration relation, we have vector error correction model and Johansen test to run. So key time series regression trend, we have without integrated of order one, everything discussed before can be described by VAR one. So and VAR one can be solved considered consistently and efficiently by least square, and thus have not different with ordinary regression with possible serial correlation. Deterministic trend and stochastic trend will cause spurious result in regression due to integration of order one residual. So trend can be eliminated through differentiating, but co-integration analysis provide a better alternative when applicable. Stationary series can be modeled with linear regression directly. Series with stochastic trend can be modeled by order Q differential. So what we have done so far was to present to you theoretical foundation of valve model. And now you know how to estimate which method you to use in order to estimate the valve model. And we now showing you after an estimate of GDP growth rates in function of term spread. And as following the discussion on the non-stationarity of GDP growth, we use data from quarter one of 1981 to quarter four of 2012. So the two model equations are given on your screen, in which we express the GDP at current time in function of lag 1 and 2 of GDP and term spread, as well as term spread of current term, which is expressed in linear combination of GDP and term spread of period of lag 1 and 2, as without forgetting error term in every K. So it's used as is done in VAR vector autoregressive model. So you see the specification which comply with theory that we just shown to you a little bit sooner in this video tutorial. So after estimate using maximum likelihood method, we have the estimate of every equation. In the left hand side of your screen, you have the estimate of GDP at time t, which is expressed at in function of our lag variable, different lag variable of period 1 and 2, lag 1 and 2 lag variable. So we have in the first in the first column, the second column, the coefficient, the estimate coefficient. We have in the last column the p-value, which measure the significance of every coefficient. We have the coefficient of growth of lag 1, which is 0.28, and the level of significativity is 10%, as is the same for GDP growth lag 2, as well as term spread of lag 1. The lag 2 term spread is the only variable that is significant at 1% rate, and you can interpret the coefficient of term spread of lag 2 term spread as an elasticity, which means that when the the lag 2 term spread increased by 1%, the GDP growth of current period increased by 1.32%. Which means that making an action in term spread will wait for 2 period of time, which means a half of year, in order to see a reaction of GDP growth. If you take a level of significativity of 1% or 5%, as well. In the second, in the right hand side of your screen, you have an estimate of term spread of current period in function of lag of different two variables, which are growth rate and term spread. So the only variable significant at 5 and 1% level is term spread, is lag term spread, and the coefficient in what is 0.5, which means that when the term spread, the lag term spread increase by 1%, the term spread of the following period increase by the almost 1%, almost the same rate. So you don't need to wait for 2 periods in the previous case, but 1 period is sufficient to have an action of variation of term spread on of lag term spread in term spread, which is the dependent variable in this case. So after this estimate, we can substitute our coefficient in our equation to obtain the linear representation of GDP and term spread in function of different lag variable, and you see different constant, different coefficients that are put into the equation, and the function VAR, the VAR function can be used to obtain the same coefficient estimate as presented above, since it applies ordinary least square equation 2. So this equation can be used in order to make prevision as well as simulation. So we can make simulation. Elasticity, as I told you, can be used in order to see what is the effect of dependent variable while our independent variable fluctuates. So VAR model can be used to measure the impact of a variable of another and the size of the impacts. as well as prevision that we are going to just present to you right now. And a prevision is used in a direct multi-period forecast that forecasts each period into a future using a model of YT and an additional predictor XT with P lags. In some, it's done first estimating our variable YT in function of previous uh, preview observe variable in this manner that you can see on your screen, which is then used to compute the forecast of y at the period t plus h based on observation through period t. And so the direct multiple period forecast, for example, to obtain 2 quarter ahead forecast of GDP growth and the term spread, we first estimate the equation GDP in function of other lags variable as well as term spread, and then substitute the value of GDP growth of term of 4 quarter of year 2012 as well as GDP of quarter 3 at the same year, the same situation with term spread and both in both equation. And when after this substitution, this is very easy done manually, but generally software have section that allows you to make prevision based on model. We will start from show you how to test unit root in series. After show you how to test unit root in series, we will show you how to estimate a VAR model. A VAR model. After a VAR model, we will also show you how to test cointegration as well as testing for lag structure. After cointegration, we show you how to finally run a vector error correction models. So you have your data imported from in Eviews. We have to, for example, to measure the impact of debt on GDP, on growth. So as variable, we have GDP, we have commercial openness rate, we have GDP per capita, we have inflation, we have the ratio debt over GDP as a variable of that we are going to use in our models. So the aim is to show to see whether or not debt have an impact on GDP. Is a macroeconomic model that we're going to estimate right now in order to make policy recommendation. So we first of all going to test for unit root test. Our first variable in the database is commercial openness. Open our data. We came in the tab view, and then we can, for example, look at graph of our variable. So we came on view. If we are going to test for unit root, we came for view and we click on unit root test. Unit root test. So we can test for. We have the possibility of choosing many tests. We have decay Fuller test, augmented decay Fuller test. We have decay Fuller test. We have Phillips Perron test. We have KPSS test, and so on. So for this example, we'll let the default value in use, which is augmented decay Fuller test, and we can test for level. The first difference, we can test for second difference, stationarity. So you will test for first for level unit root test. So we click on OK, and we have test result. So we have a p-value that is higher, and if we fix the threshold of significativity of 5%, we can we can we can accept the null hypothesis, which is commercial openness rate has a unit roots. So our series commercial openness is not stationary. So let us back in that view and go back on unit root test. If we choose unit root in first difference, we see that our p-value is smaller, so that we can reject unit root test, which is that our theory have unit root test. So our theory is stationary in difference. So that's the result of our test. We'll let this variable, let us look at GGP. GGP, we came on view, unit root test, back on first difference. Okay, we see that our series GGP is not stationary, because the p-value is higher than any threshold that we can choose for significativity. So we can look at the unit root at first difference. We see that our series is stationary, even though we chose 1% threshold. So we do the same thing for GDP per capita view, unit root test, and in first difference we look at, we can see that our theory is not stationary, because the p-value is very significant. So we can look at first different tests, and we see that our theory is stationary in difference. So we can look at inflation. We have unit root tests in different, and the unit root tests shows that at 5% level we can affirm that inflation is stationary, because we reject the null hypothesis, which is inflation has a unit root test. So for now, only inflation is stationary among our variables. We look at ratio of debt over GDP, the ratio debt over GDP. We look at unit root tests, and we can see that the series is not stationary according to the p-value. So in first difference, we can see that the series is stationary when we choose 5% threshold. So now that we have different unit root tests and the situation of each other variable, in our model we're going to test for the impact of debt on economic growth. So we're going to use GDP and ratio debt on the GDP as dependent variables, and other variables will be used as covariants. So when we want to estimate a VAR in Eviews, the first thing to do is to go in the tab quick and go to estimate VAR. So we're going to first of all estimate standard VAR. Endogenous variable are, as I told you, GDP, GDP, and you just put a space and you put as your second endogenous variable, which is ratio uh, ratio debt on the GDP, which is a variable that will be used to capture debt information on debt. Endogenous variable, we are going to put it in this interface, and you see that Eviews chose the constant as a default endogenous variable. We let it like it is, and we will add other endogenous variable that will help us explain the impact of debt on GDP, on economic growth. So our first endogenous variable is GDP, commercial openness. So we will differentiate the commercial openness because commercial openness is not stationary. So let's notice that our variable GDP and debt are stationary at first difference. So we'll estimate first of all the var without before seeing if our two variables are co-integrated, if we are going to estimate an error correction model. But in endogenous variable, we will differentiate variables that are not stationary. So we differentiate the commercial openness. The second variable is GDP per capita. We also differentiate it GDP per capita. And finally, we have inflation, which is stationary. So we will not differentiate inflation because inflation is stationary. So after introducing all these parameters, we just click on OK, and our VAR model is estimated. We can see the first equation, which express GDP in function of lab 1 and 2 GDP, and as well as ratio of debt over GDP with additional exogenous variable, which are differential of commercial openness, differential of GDP per capita, and inflation, that are our dependent exogenous variable in our model. So we have the R square, which is close to which is 99%. We have other estimate parameters. So we have the two equations, the equation of GDP in function of other variable, and the equation of ratio debt over GDP in function of. So if you come back on estimation, you see that for default, lag interval for endogenous variable is 1 to 2 lags. So we'll go to test a lag structure to see what is optimal lag that we need to introduce in our model in order to make it optimal. So we'll go in view and go in lab structure and choose the last option, which is lab length criteria. So in our model, we will put 3 lakhs and click on OK. You can put, for example, 5 lakh, and click on OK. So you will see in our model that the optimal lab structure is uh, is 2 here. The star mean that the optimal uh, so we can come back on our lab structure. First of all, we will put 3 as a lab to introduce in the model, and we see that lab 2 is the criterion that optimize according to other the 2 lakh is the best number of lakh to introduce in our model according to various criterion uh, uh, that are sequential modified LR test statistic, final prediction error, archaic information criterion, Schwartz information criterion, and Alan-Quinn information criterion. So we will put in our VAR a 2 lakh as is indicated in by default by Eviews. So we have our VAR of 2 lakh that is estimated with the O ratio. As you know, our independent, our endogenous variable GDP and ratio are stationary, are not stationary, so we will test for cointegration of the two variables in order to see whether or not we will estimate a VAR model, so a vector error correction model. So we look at view, we go in cointegration test and we click on OK. So there are too many possibilities. So the default value is trend, intercept, no trend, in constant, and VAR and test VAR. So that there are too many options. You can put no intercept in your or trend in your VAR. You can have intercept, no trend. So you have to choose uh, different option among others. So we choose the option intercept in our series and click on OK. So you should see that trace test show that indicate that there is one co-integrated equation at 5% level, which means that we will estimate a vector error correction model as well as far as there is a one co-integration equation between GGP and the ratio depth over GGP. So now that everything is set, that there is error correction model that we are going to estimate due to the fact that there exists a integrating equation between GDP and ratio depth over GDP. So we're going to show you how to run error correction models. So we have estimate a VAR model. A VAR model, this is the equation of the VAR model. After that, we will just go to estimate and choose vector error correction. Vector error correction. Remember when we were doing a tutorial video on the theoretical part of vector error correction model, In VAR model, we saw that when we estimate a standard VAR and we are going to pass from a VAR to a vector error correction model, we differentiate our independent variables so that if our VAR were lab P, error correction model will be on of lab P minus 1 so that you know that we estimate a VAR 2 model, and now we are going to estimate a vector error correction model associated to our VAR model, so that we should estimate a VAR 1. So the lag interval is 1 1, not 1 2 as it was in VAR model. So we are in vector error correction model. We choose the option vector error correction model, and we decrease our lags by 1. So we had VAR 2. Now we must have vector error correction model of lag 1. So after that is set, we click just on OK, and we have our VAR, which is estimated here, which give a R square of 98%, more than 98%. So we have cointegration equation, which is given by GTP minus 20008.0.4 time ratio depth over GTP plus a constant. This is cointegration equation that is used in order to express manual. We have the expression, the first equation that expresses the differential of GGP in function of cointegration terms and lag 1 GGP. And problem here is that we cannot use it in order to make to see whether or not each variable is significant, statistically influence significantly dependent variable, which is the differential of GGP. So we estimate the error correction model. We'll estimate an error correction model in which we'll estimate an error correction model in which a linear model a linear model in which we will introduce every coefficient here, and we'll look at student tests of each coefficient to see whether or not each coefficient is significant, to see whether or not don't forget that at the beginning of this tutorial, I told you that we're going to evaluate the impact of debt on the economic growth, so that we choose as measure of economic growth the GDP, and measure of debt ratio debt over GDP. So we have our cointegration equation. As far as cointegration equation appear in the linear model that we will express, we'll just generate the error correction term that we will use in our linear model. So we just go on generate, we generate cointegration equation, which is equal to GDP minus 2. This coefficient which is here is 20080.4 time the ratio debt over GDP plus the constant of the cointegration equation, which is 378486. So we just click on OK, and we have the cointegration equation which is generated. And now I will estimate my linear model to better see significant and better use it in order to make maybe simulation or forecasting, for example. So I go on quick estimate equation, the principal, the dependent variable will be GDP, 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 not GDP, but the differential of GDP, because in VAR model we differentiate our dependent variables. So we differentiate the GDP as dependent variable, which is following by dependent, which are cointegration equation. You know that in VAR we make cointegration equation is lat. The second variable is the differential of lat GGP, lat 1 GGP, lat 1. The third variable is the differential of lag ratio debt over GGP. The differential of lag ratio debt over GGP. The constant and the difference other equation in our model, which is the differential of commercial openness, the differential of GDP per capita, and finally the inflation. So we have our linear model and click on OK. You see that our linear model have the same coefficient as in our VAR model, but we can observe the significance of each coefficient here, so that we can say that the cointegration coefficient is negative and significant, which is the expected sign in error correction model. We have the lag GGP differential of GGP, which is not significant, and we see that the depth, the lag depth significantly influence on GGP, so that we can conclude that debts have a negative impact on influence significantly on GDP, and the impact is negative when we look at differentiated variable. So we can also see that in a variable that GDP per capita and inflation have significant impact on the GDP. Impact is just positive impact. So you can use it in order to make a forecast if we have correct prevision of variable like which are not lacked, such as commercial openness, GDP per capita, and inflation. So if we can make a prevision of commercial openness for this the current for the next year. The also the provision on GDP per capita and inflation. You can make a prevision forecast on different dependent variable. So that's it for today, and I hope this tutorial very what you useful to you in the understanding of GDP of sorry in the understanding of VAR and VEC more. See you very soon.